We are live. Hey everyone, we're here for our next session. We have Tomas. He's a researcher from crypto.com. He'll be doing a talk on secure enclave signing backend for Tendermint KMS. And I'll let him take it from here.
All right. Hi everyone, wherever you are, and well done if you made it all the way up to here. So yeah, thanks for the introduction. So just maybe one initial disclaimer. So even though I'm here as someone from crypto.com, things I say here, they are not opinions or official, views of crypto.com. So the legal team asked me to give these extra legal disclaimers. Anyway, so first small advertisement. So at crypto.com, we've been active in the Cosmos and Tendermint ecosystem for a while, so we've been using it and also contributing to it. So if you're interested, you can check out the crypto.com GitHub organization. There's a few repositories you may be interested in. So there's Chainmain, which is crypto.com chain, which has most of the things you expect from a Cosmos SDK-based chain, but we have a few custom tools like a PyStarport, which is kind of Python version of Starport, and the integration tests using the Nix deterministic builds and stuff like that. So Naristaller, which is the original crypto.com chain prototype, which was built with Tendermint RS and RS APCI. And this is not an open source, but it's going to be soon. It's kind of a tool for processing Cosmos SDK events for further usage. So for example, for block explorers and stuff like that. So, and final note is we have a dedicated channel on the Cosmos Discord. So yeah, feel free to join us and keep an eye on it. I think I'll announce when the chain next is open. And also next week, we'll probably have an announcement regarding incentivized testnet. So the validators are always welcome. And for more information, you're welcome to go to chain.crypto.com/docs. All right. Let's now dive into the topic of today's talk. So it's Tendermint KMS and the secure enclave. So I'll first talk about the Tendermint KMS, just a sort of brief introduction, and then we'll move on to the technology itself and the secure signing. So with Tendermint, I think some of you may know that you need to have a hotkey that's used to sign on the consensus messages, like vote proposals, votes and things like that. If you're living on the edge, you can use you can have the key in a plaintext file. But for like a more robust setup, the Tendermint provides this preval interface, which is then used to sign on these messages. And Tendermint KMS is kind of a reference implementation for this signing interface. And it provides various backends that it serve as the front end to this preval. And in the official Cosmos app documentation, it kind of mentions that there's no recommended solution. They have different trade-offs, and we as the community are encouraged to try to improve this state-of-the-art on the key management side. So this is what this talk is about this part, another option for this part. So one maybe first thing you may ask is why would you want to use Enclaves, since there are already quite good options on the hardware security module side. Maybe first reason maybe it's quite cost effective. So for Intel SGX, that's an instruction set that's available in most Intel CPUs. So if you already purchased a server that is a Xeon CPU, then why not you leverage the instruction set there. Other technologies, for example, I'm going to cover is AWS Nitro Enclaves, and they come without any additional costs with the standard EC2 instances. So when you have a 4U CPU instance, you can leverage Nitro there. That's about say $70 roughly. Whereas if you leverage some external signing service, like say on AWS, you have Cloud HSM, it's much more expensive. The other reason is that unlike some HSMs where when you give it a signing payload, it will just kind of sign on everything. Here you have a fully programmable logic without many limitations of the embedded hardware. So you can have a more you can aim for some other invariants in what is being signed on. So in particular here for the context, it would be, say, some invariants around the consensus algorithm, that the messages have the right format and things like that. And lastly, like if you have some cloud infrastructure, like it may not be that easy to have HSMs in that setting, like especially if it's dynamic, where you need to spin up machines in different regions and so on. So Enclaves could be a kind of extra hardening measure on top of something else. So for example, threshold signing. All right. The questions, so I'll dive into the, just feel free to, if you have any questions, just feel free to ask immediately. I'll try to, sometimes I'll go over stuff quite quickly, so I may go back and explain it better if you're interested. All right, so if there are no questions, I'll dive into the topic. So first would be kind of general introduction into the enclaves. So in the context of this talk, we talk about these trusted execution environments, or TEs. And by that, we mean some features on the CPU that are used for code and data isolation. Usually it's some confidentiality and integrity guarantees. And there are many different technologies from different vendors, and they have different approaches and different trade-offs. So I kind of roughly divided it into these three. One is on, say, CPU mode level. Typically, say, for example, ARM trust zone. So in your smartphone, if your smartphone supports some kind of a keychain functionality, it may be leveraging this technology. And what it does is it would isolate the code execution and its memory from the OS kernel, but not from other enclaves. Typically, so there might be some other like system on chip that don't that may have some extra features, but anyway. Another is kind of on the VM level. So that's, for example, what the AMD technology does, and also the AWS Nitro enclaves, where you have different VMs and they have encrypted memory and are separated from the hypervisor as well as the other virtual machines. And lastly, it's kind of more fine grade. It's on the process level, where the enclave is executed. Execution is isolated from the operating system as well as other enclaves. So that's typical for, say, Intel SGX. Kind of one common concept that I would briefly cover when we talk about TEs and this, say, trusted execution environments is attestation. And what people mean by that is when you have some enclave application executed, and you have some external party, it could be a user, service, or something like that, and which try to connect to that enclave application. The enclave application can produce what's called the attestation report, which will contain some some measurements of the execution as well as cryptographic proofs to verify the authenticity of the execution. So the service can check that the presented measurement as well as the signature and things like that are correct. Typically, it's done through PKI certificate chains, where the hardware vendor is kind of the root of trust, but it could be more flexible. So, for example, in SGX world, there's this in the second version of SGX, there's a data center attestation primitives, which kind of make it less dependent on the Intel infrastructure. The second concept, which in the context of Dictos only applies to SGX, is ceiling. So typically the trusted execution environments, at least the ones we cover in this talk, they don't have any persistent storage. So if you shut down your machine, then you lose all the data, which may be a bummer for many applications. So you may want to persist the state outside of the trusted execution environment. So you would persist the state in the untrusted execution environment. So in order to be somehow to preserve the guarantees of the trusted execution environment, you need to encrypt it in a way that only the particle enclave application can decrypt it. And this is always done in SGX. So there's some kind of a key that's fused on the CPU, and if you wanted to kind of get that key, like you destroy the CPU. And there's some kind of other parameters that are, for example, the enclave measurement or the signature of the enclave application and so on. They are used as a kind of input to some key derivation function that will give you unique key that only the enclave can derive on that particular machine. So it's always per CPU. And if you're interested more, there's a great blog post series by the Quarks Lab, so they go into more detail about some kind of internals and externals of the SGX. All right. So that was briefly it. I think there are so far no questions, so I will dive into the Intel SGX. I think most of you have heard of it, so there will be just kind of two things I want to touch on. First is how to program like in Intel SGX. So it's basically the same instruction set as for Intel CPUs x86, but it has some quirks. So it's not easy to, if you have a language that's a runtime like a Golang, it may not be that easy to port it to it. And luckily for Tendermint KMS is written in Rust, and for Rust there are many options how we can program Intel SGX applications. One approach is with some sort of high-level framework. So there's a few of them. They roughly work in a way that they will compile your Rust code to WebAssembly, and then they have a WebAssembly environment inside an Enclave that will execute it. And they have some other primitives for attestation and so on. Then there's a project started by Baidu, Apache Enclave, which is both like a low-level wrapper or around the official Intel SGX SDK, which is, the original SDK is for C and C++, so it's kind of a Rust wrapper around it. They also provide a high-level framework in a similar manner to the other ones. That one is quite good. I think it's a good starting point. One kind of bummer there is if you use a standard library, or if any crate that you depend on uses the Rust standard library, then you need to port it to their kind of own versions of it. And lastly, there's a company called Fortinix, and they have their own custom, say, SDK. And it's already in the Rust compiler. So if you install this target, x86, Fortinix, or no SGX, then that's all you need to do, basically. Then you take your Rust code and you can compile it kind of for SGX and use their runner for it. You have a bit different kind of programming model than what's inside the Intel SGX SDK, where in the SGX SDK you divide your code into the out of Enclave calls and Enclave calls, which are C functions and so on. Here it's kind of operating on byte streams. So I will cover that in a moment when I talk about how it's done in the KMS. I think in some of the previous talks, someone touched on the attacks, so let's cover it too. So in some sense, SGX, you may have heard of it from tech media, that maybe every few months there's something. And in some sense, it's good that I think we know the limitations of the technology. Kind of we can be sure what it can do or it can't. And naturally, it has quite ambitious security goals. This kind of process level isolation, but there's the reality of the complex, CPU architecture and the complex even computer architecture with various interactions inside. And luckily, Intel was kind of forward-seeking, so most of the attacks they can be mitigated by either CPU microcode updates or some settings in BIOS. So, for example, disabling hyperthreading and things like that. But there are two attacks that we as software developers we still need to worry about. So one is LVI. I think if you haven't heard of it, I think I recommend you to check out their website. They have a very cool movie trailer for their paper. And and the thing about LVI is that most of the CPUs on the current market, they are vulnerable. Luckily, the latest LLVM has option to mitigate this type of attack, and it's already shipped by default in a recent Rust compiler version. So if you use the Fortinix EEP, it will automatically use these compiler flags on the LLVM to mitigate this attack. The other is also quite recent, is Vault Villager. You may have heard of what was it, Vault Plunder, so this is a similar type of attack, also under vaulting, but Plunder Vault work on the software level, so it can again be mitigated by disabling undervaulting in BIOS. But for this type of attack, it's working on the hardware level, so it can't be easily disabled. But the thing about this is it requires physical access, so it's kind of like a question maybe for a validator to evaluate whether, say, malicious cloud provider is in your threat model. And There are some possible mitigations. Nothing is 100%, but for example, if you make use of say synthetic nonces, so they would make this attack or all these like a fall injection attacks more much harder. All right, so this is how the prototype for the Tendermint KMS works with the Intel SGX. So we have the similar thing. So we have the Tendermint node, which submits this request for signing, and the Tendermint KMS has this SGX runner, which is the host process that takes care of the things like launching the enclave and forwarding the requests. And this is using what's called the user call extensions in the Fortonix platform, which basically is kind of a byte stream that the SGX Enclave we would connect to some TCP connection, but it's not really a TCP connection. It's more like this interface to talk to the host process. And then there's the Enclave app, which does the signing. And it's using of the sealing mechanism that I described before. When you shut down, then you can. So first time you generate the key, you will put the sealed validator key to the runner. They will persist it on the disk, and then next time you run it, you will try to load it. So at this moment, it's very plain, simple prototype. I think I'm currently working on extending it to run more of the enforcement invariants inside the SGX app. And one kind of a thing, maybe a warning, is the sealing is a cool functionality, and you may want that, but in some cloud settings, it may be troublesome because the cloud providers, they typically don't guarantee hardware affinity. So one day your one day they relocate your VM to a different machine with a different physical CPU, and then you can't unseal it because that CPU won't be able to derive the same key as the previous one. So I'm kind of this is still being investigated. So if you have some good ideas or some thoughts on how this can be addressed in say general sense in a cloud setting, then you're welcome to share it, say on Discord. Also, I think Azure, they are working on some solution, but it's not yet ready. All right, I think so far no questions, but yeah, feel free to write anything. And I will then move on to the AWS Nitro Enclaves. So I think they recently came out to the general availability on EC2, so you can use them almost anywhere. It was recently means maybe end of October. And the thing about them is they use the same hypervisor technology as what's used internally in AWS for EC2 isolation. So if the reason why you can't read other people's instance memory, that's also leveraging this technology. And I talked in the beginning about this different approaches. So this is kind of the second one with VM-based isolation. So for your application, you need to kind of take into account that Linux kernel is also in your trusted code base. And one other thing is that you kind of the way it works is you launch this mini VM inside your instance. So you need to dedicate it some CPU that you have. So you need at least 2 virtual CPUs for that enclave. So the parent instance needs at least 4. And just like so, the enclave doesn't have any I/O. So in the production mode, you don't even have a console output. For the debug mode, you have a read-only output. And if you want to do some I/O, then you can only communicate with the parent instance that launched the enclave via this interface, which is kind of bind streams similar to like a TCP connections or Unix domain sockets or VSOC. And there's no kind of equivalent of sealing that exists in the Intel SGX. So what one does instead is you can leverage some services. So for example, for the AWS, they have a key management service, and where you can specify policies for like encryption, decryption, generating data keys, and so on. And you can have a key policy that will enforce the attestation. So in that key policy, you will specify that you say for this particular action, for this key, you only want this enclave with this, measurement to be able to execute this API. So that's how one would do it. That you would call this service probably to, encrypt or decrypt the data, and it would be enforced on this key policy level. And this is how the Tendermint KMS looks with the Nitro enclaves. So as I mentioned, you need to factor in the Linux. So similar to like say Docker containers, you can think of it. You have this Nitro enclave that's running some Linux distribution, hopefully some minimal one, and in it you have the Tendermint KMS, the app. So the first thing you need from the outside is some configuration. So that's inside the parent instance, you would have one step kind of to push the config to know what to connect to, what's the chain ID, and things like that. Then you have a proxy that will proxy the requests from Tendermint to this interface, the VSOC. Then you have another proxy that will take care of the state. So it will, whenever there's an update in the internal update in the TMKMS, it will send it and we'll try to persist it. And finally, so in the config, you would have the encrypted validator key, and it needs to have a way to decrypt it. So it needs to contact the AWS KMS, as I mentioned, or HTTPS. And Amazon, they provide this VSOC proxy tool, which just forwards the traffic. So it's automatically configured that you would run it, and when inside your enclave you connect to this VSOC, it will kind of forward all the traffic to some external endpoint. Okay, so these were the two technologies I wanted to cover with the Tendermint KMS. So let's somehow conclude this talk. So from these experiments, the Enclave seems to be a viable option for validator signing backends. They have different trade-offs than what you have with traditional hardware security modules. So I mentioned in the beginning that one advantage is you can have a more flexible validation logic that you can program. The con maybe kind of say in traditional HSMs you have some tamper detection generally, that when someone tries to basically attack the HSM, they would typically it won't be that easy, or they would self-destroy or something like that. And even within this space of just the execution environments, there are different trade-offs with different technology approaches. So for SGX, kind of one advantage is that you can run it on your own hardware, and you also have many vendor choices. So Azure, they have the confidential cloud computing, IBM, Equinix, and so on. And also you have a low trusted code base because it's on the process level. So it's, at least from your software side, it's only only what you use is kind of in the trusted code base. But there are some potential isolation weaknesses. I mentioned the attacks that usually you may, if there are side channels and things like that, and also hurdles. So for the first version of the Intel SGX, you need to, if you want to launch it in a production mode, you need to sign it with a key that was approved by Intel. So again, in the second version of SGX instruction set, this can be again more flexible. They call it flexible launch, but it's not supported by all the CPUs in the market. And with the Nitro enclaves, there's different trade-offs. So you have a single vendor. I don't know if Amazon plans to make this technology available to outside AWS, but so far I don't know. And you need to take into account this higher trusted code base because you have also Linux kernel in there. But at the same time, this is something that's been used for EC2 isolation itself, and there's a great tooling around it. Yeah, and I plan to work on this further, so it depends on some interest and feedback. So there's definitely room for improvement in these initial prototypes, and make it more ready for production deployments. And if there's enough interest, maybe it can be even, say, there could be first class support in Tendermint, something like the Prival connection can connect to vSock directly instead of using the proxy, or having an option in Tendermint to specify the attestation parameters that you expect on the connection. So that's more or less it. Here are the references if in case you're interested in the attacks. The LVI was it's this one. You can also search for LVI the website, and we'll just this one. And yeah, so thank you for attending this talk. I think it's been 12 hours for everyone, so I see many people maybe a bit drowsy, but thanks for coming in and listening to my talk. And yeah, I think we may still have a few minutes for questions, so just feel free to drop the question in the chat, or ask a question in the Q&A. Otherwise, after we are cut off, I will still hang out on the I will still be on the Crypto.com channel, so either feel free to direct message me or just drop a message there, and I'll get back to it. Cool.
All right, cool. This was a really great talk. So we're going to probably wait another minute, I guess, or so to see if any questions come in. If not, we can transition to our next talk. Do you have a Twitter handle in case people want to ask you questions if they come up with anything later, or in case you want to share slides?
I do have Twitter handle, but I'm not a very active user. So I think the best thing is Tomtau, TOMTTAU, on the Cosmos Discord. I think that's the best. I can write it in chat.
Yeah, that'd be great. Okay, perfect. Well, thank you so much for this really great talk. We're going to transition to the next session then.
Okay, thank you.
All right.